Okay, so I'm going to talk about implementing distributed programs. So before this, you have had some lectures on distributed algorithms. So I wanted to know exactly what you have done in that. So what are the kind of distributed algorithms which you have seen so far? Reader? Leader election. Okay. Then? Fault tolerance. Okay. Then? What about yesterday? What was? I see. What do you mean by fault tolerance? That's not clear to me.
Like what happens when a link fails? What happens when a
Okay. Okay, fine. So did you do? Okay, but you didn't do something like Byzantine agreement or something like that.
Yeah. We did.
Okay. Consensus did you do? Okay. Fine. So these are distributed algorithms, and I am going to be talking about distributed programs. Okay. So what I mean by that is that we are not really only interested in just the kind of overall idea of the algorithm, but we actually see how that program is going to be implemented in some programming language on some real computer and so on, right? So that's what we are trying to do. So things will be a little more detailed, but what we'll do is we won't consider very sophisticated algorithms, we'll consider fairly simple algorithms so that the algorithm is clear immediately, and then it's a question of how do you actually implement that algorithm on a program. So so maybe in this style, let's just consider some problem. So one very famous problem is dining philosophers. Okay, so how many of you have seen this before? Dining philosophers? Quite a few of you. Okay, so so the basic problem is very simple, that you have this table and there is some noodles or something like that, and then there are 5 forks here. Okay, and then there are 5 tables here, and there are 5 philosophers, and being good philosophers, they spend their time thinking and sometimes eating, and each of them has a fixed table. So this is, say, I don't know what, table number 1, 2, 3, 4, 5. So the philosopher will be thinking, and when the philosopher wants to eat, then he or she will come here, eat and go away. The only problem is that the eating this noodle requires using both forks. Okay, so that philosopher has to pick up both forks and then eat the noodles. Okay, I don't know what they do about washing the forks, but there must be some arrangement they have there, right? So they have this kind of thing. So the point, as far as we are concerned, to note is that when philosopher 1 is eating, at that time philosopher 2 cannot eat because the right fork is not there, and philosopher 5 cannot eat because the left fork is not there. Okay, so they have to wait until philosopher 1 finishes eating, but eating is not supposed to take a lot of time, so and that person doesn't mind waiting, and then eventually gets to eat. Okay, so this is the problem. It's okay. It's of course a completely ideal and silly kind of problem. So why do you think we study this problem at all? And why is it interesting for us as computer scientists to study this kind of problem? what kind of real world features are we talking about when we are talking about this problem? Yeah.
Have limited resources and how to distribute
Limited
resources
huh?
and how distribute in such way that any with the maximum output. They say
Okay.
basically sometimes
So can you give an example of such a problem?
like when the philosopher one is there, they make sure
No, I don't mean philosopher problem. I mean in computer science, a problem which you encounter, which we can model as the philosopher's problem.
E-banking, online transactions.
Yeah.
Now, it like suppose there are two parties A and B, and A is depositing some money, and at the same time, suppose B is doing something else with his account. Say
Yeah.
he is withdrawing some money. Now, but both of them are basically using the same resource, so that might give rise to some discrepancies if it's not carried out properly.
Okay, that's very good. That's actually an example I'm going to use later. But that is so what you are saying is, supposing you have two people or more people, at least two people, sharing a resource. Okay, fine. Supposing this is your problem, then how does this model that?
When one is accessing it, the other will not be allowed to make any changes to that resource.
Correct. Yeah. But there is also something else which is going on here, which is that while one is eating, okay, 2 and 5 cannot eat. That's true. But 3 and 4 can eat, or at least one of 3 and 4 can eat. So there is something else which is there, which has to do with the fact that there are 5 philosophers, and if there are only 3 philosophers and when one was eating, then the others are just stuck. So how does that reflect in your online transactions model?
The resources over here is like more, so probably that's why.
The resources?
You have 5 folks over here.
Yeah.
Over there you are accessing the same one particular resource.
Yeah.
So,
Okay. No, but just think of having, I mean, so this also you can think of the fact that there may be lots of resources. I mean, in your particular example, there can be many bank accounts, right? So 2 people might be trying to do something with the same account, right? But at that time, some other person can be working on some other account. That may not be a problem, which has perhaps nothing to do with what is going on here, right? Or there may be one account, you are withdrawing with your ATM in Chennai, okay? So maybe the money goes from your Chennai account, but somebody else is withdrawing something in Calcutta, okay, from their Calcutta account, and these two are not related in any way. Right? So yeah, the traditional example for this which is given is operating systems. Okay, so these you think of as various jobs which are running in an operating system. Okay, and these resources you can think of as, I don't know, hard disk or printer or whatever kind of things, and it might happen that a particular job needs 2 resources or 7 resources or something. So this is just to model this kind of problem that we are talking about. Okay, so one particular process is using, or one particular job is using a certain number of resources. Okay, and those resources could also be used by some other process or some other job. So there is therefore contention for these resources. So there is and that is what we are trying to model, that there is contention for resources and how do we manage that. Okay, so that's the operating system's motivation for this problem. Okay, so for the moment now let's forget about the operating system things and we'll come back, we'll just think about these dining philosophers. Okay, So you have this solution, and now, I mean, we have this problem, and we have to find a solution for it. Okay. So how would we solve this? So now you think of these philosophers as actually some kind of program. The philosopher is just some job which is running somewhere. So I would say so I will model, for instance, this particular thing which a philosopher does is, so here is a philosopher. Maybe I should put something else. Right. So this is what the philosopher does forever. Okay. Philosopher thinks and eats. Okay. So as I said, as a distributed algorithm, this is trivial. There is no complexity in the algorithm. But what we are worried about is how are we going to actually implement this in a system. Okay. So okay, so there's nothing much to do about thinking. The philosopher just thinks. Okay, so the difficulty lies in eating. Okay, because eating is a more complicated process. So we can split it up into 3 parts. Actual eat. Right. Okay. So you just pick up the forks, then you eat. Okay. And again, that process of eating we are not interested in going into further detail, right? And then you put down the forks. Okay. So why is this not a suitable program? I claim that this is not good enough for the purpose of solving this problem. Okay, so you have to do something if the fork is not available. So what shall we do? I can write? Yeah? Okay. Okay. Yeah, so this is complicated because first of all there are 2 forks. Okay, so let's first split this. Similarly, this will become is this visible? What I am writing? My writing becomes worse and worse as time goes on, so you have to tell me, right? So, okay, so yeah, so let's say, I mean, there is no reason to choose left over right, but supposing this is what we decide. Okay, so now the question is, now you want to do get left fork. So how will you do get left fork? So as you said, you have to first check whether it's there. Yeah, what do you do if it's not there? If it's there, of course you pick it up, right? If it's not there, what do you do? Okay, let's see. If right, yeah, so this is okay. If they're on the table, there's nothing to do. Okay, so the question is, what do we do? So you're saying else wait, right? But now we come to a problem, which is that, okay, you wait. What does wait mean?
You wait till that fork is available.
But how do you know?
Till the person to your left has put it down. When he's finished eating,
Yeah.
you wait till that.
Okay, but now, okay, so now you're thinking like a human being, but I want you to think like a program. Okay, so what will the program do? Yeah.
We'll program it in synchronization of force.
Yeah. What does that mean?
In operating systems, like we'll put it in a wait condition, and once it is it gives signal, the one which is using, we will then put it up.
Okay. So what is this wait condition and signal? Who does this?
That is an atomic program.
Yeah, but how do you get it?
We have to program it.
Huh?
We have to program it.
Right. So normally what we do is we ask, there is an operating system. So we ask the operating system saying wake us up when the fork is available, right? But now this program is actually the operating system. I mean, it's part of the operating system code. So you cannot ask this program to say call somebody else, right? So the question is, how do we actually do this, right? Yeah.
There is a clock and we can have a predefined value, and after every cycle we can have it.
Okay.
Clock is coming in.
Okay.
There is a clock.
So you have this clock, let's say. So let's say every minute you want to do something. What do you want to do?
Like we can give to read 30 seconds. So if
By the way, this clock, right? It's a little, okay, yeah.
we start at some first cluster,
Yeah.
then we will check after 30 seconds. We will see, we'll make sure that the second cluster picks the fork at that time. And like after every 30 seconds, the other cluster can get the fork.
No, so far we are just talking about one philosopher. Okay, we'll worry about the second philosopher later. Okay, so supposing you want just one philosopher, right? So what should this one philosopher do? One philosopher picks up the fork, looks at the table, okay, finds that there is no fork. Okay, now what should the philosopher do?
Wait for 30 more seconds and then check again. Because everything happens in 30-second period assuming.
Okay, so what you are saying is we put this inside a loop. There is actually true condition. Yeah, so something like this. Okay, but that's a different solution.
But it can happen that in the 31st second the left philosopher leaves the fork, and in the 32nd second the left philosopher again picks up the fork. So
No, here that doesn't happen. Here you have to wait for 30 more seconds. So for 29 seconds the fork is just lying on the table, right? Is that, is that correct, or you had something else in mind?
30 seconds is a big wastage.
Okay. No, did you mean the fact that the philosopher puts down the fork and again picks up the fork?
Yes, no, the left philosopher himself puts the fork, say, in the 31st second.
Yeah.
And the left philosopher again picks up the fork in the 32 or 33rd second. Before
Okay.
that.
Why would the left philosopher do that?
I mean, say if he has stopped eating in the 31st second, he leaves the fork, and he again gets hungry in the say 32 or 33 second, he again picks up the fork.
Okay.
So this philosopher didn't get a chance in between.
Okay. No, so that's a good problem. That's definitely a problem. But let's say that if since we are basically using 30 seconds as our grain of time, okay, we will say that when after eating a philosopher has to think. Okay, so we will say that this thinking is at least for 30 seconds. Okay, the philosopher doesn't get back to eating in the same 30 seconds. Otherwise, it will be, as you say, the guy might just keep picking up the fork, right? So instead we say the philosopher at least thinks for 30 seconds. Until then this problem will not arise, because we are kind of, the solution which is being offered is that we fix a certain granularity of time. The granularity of time which we have fixed is 30 seconds. Okay, so everything happens in I mean only one action will happen within that 30-second interval. So that's a reasonable assumption to make. Of course, I mean for an operating system it won't be some big number like 30 seconds. It will be some nanoseconds or milliseconds, or but whatever it is, some unit of time we can fix. Right.
So is that 30 seconds is a global clock, or is that just a local clock?
What is global and what is local?
Because like if I mean all these 5 philosophers are using the same clock.
Yes, because they are all at the same place. Yeah. So all the philosophers are at the same table. So what we are modeling using this is a kind of single processor operating system. Okay, and these are all jobs on this. So this is not a distributed operating systems where very complicated things are happening with multiple processors in many places. Okay, this by the way, this dining philosophers, I don't know, you probably know this, was invented in 1965 by Edgar Dijkstra. It was invented because he wanted to give an exam question for final exam in an operating systems course. So those poor students were the first people who suffered this example. So after that, everybody who does this course keeps suffering it. Okay, so so that's and the question was, how do you actually yeah, so this solution, okay, let's assume, as I said, I've kind of gotten rid of one possible error by saying that you think for at least 30 seconds, the error which he pointed out, right? So now, is this program correct? Will this work? So of course, just as you have expanded get left fork, you will expand get right fork, and maybe you will expand put down left fork, and you will write more detailed code for this, right? But will this program work correctly?
Deadlock between all the 5 philosophers. Suppose if everyone picks up the web for the same time.
Okay, so there is a possibility of deadlock. Okay, so what is a deadlock? Formally, what is it?
Everybody is waiting for at least someone.
Right, or you can say that formally we will model a deadlock as follows. You say that a process is waiting for a resource, and a resource is being used by a process. Okay, so if you just say which process is waiting for which resource and which resource is being used by which process, then there is a cycle inside this graph. If you draw that as a graph, directed graph, then you will get a cycle. Okay, so it need not be that all processes are waiting. Maybe some other processes are doing their job, but there is a cycle. So these philosophers or these processes which are there inside the cycle, they are deadlocked. Okay, so that's a deadlock. Okay, how can a deadlock situation occur here? Because it so happens that everybody gets hungry at the same time, right? And each of the philosophers executes this get forks, and then they go into get left fork, and then they do this. The left fork is there on the table, so they pick up the left fork. Okay, they come out of this loop, and then they enter the get right fork. And when they enter the get right fork, you face the same kind of code, but at that time the right fork is not on the table, so you skip. Okay, so then you come back here. Okay, so this kind of code is called a busy wait, right? So all of them keep doing a busy wait. Okay, right? So sometimes people say that this thing is called live lock rather than deadlock, because the processes are all doing something but yet not getting what they want, right? So it's a different way of. Whereas deadlock is when you are just kind of passively waiting, right? So, okay, so this is the problem with this code. Okay. And this is something which an operating system has to solve, because typically, I mean, it's not just 5, there are like hundreds of jobs, and this kind of things can happen. Okay. So the question is, how will you find a solution to this problem?
Solving deadlock.
How do you give a solution where deadlock does not happen?
The odd philosopher picks up the left fork first and then the right fork, and the philosopher picks up the right fork first.
Okay. Let's see. You have a solution. So so you are saying for philosopher 1, 3, and 5, pick up left fork, okay. And why is this deadlock free?
Because, like say, philosopher 1 picks up the left fork.
Yeah.
And either at the same time, philosopher 2 tries to pick up the right fork, because either one of them will win. So once, say, if one wins, then then the philosopher 2 does not start picking up the fork. But if 2 wins, then 1 does not pick up the fork.
Hmm.
So it's deadlock.
Okay. So you are saying, so okay, let's consider this. So there is contention between these two guys. Okay. So okay, then let's see. So this is for 1 and 2. So now let's see 3. What does 3 do? 3 picks up the left fork, 4 picks up. Okay, fine. Now what does 5 do? 5 picks up the left fork. Okay. So for the picking up the left fork thing, okay.
Okay, in 1, 2 case, who is who has won? If 1 is
You are saying one of these two will win, right? If you think of this as a game, right? You also done game theory before this, so then one of them wins, right? So this is an iterated game, right? So there are lots of little games happening. You win and then you go ahead and go into the next game. Okay, so one of them wins. Here one of these guys wins. Here this guy always wins. Okay, right? Okay. Now, so supposing it happens that this guy picks up, this guy wins, this guy wins, this guy wins, and now
there is problem in 1 and 5.
huh?
Then there is problem in 1 and 5.
No, what I'm trying to say is that now as far as I can see there is a deadlock. Right?
Five can finish it and then one.
There will not know cycle in the
Yeah. Five can finish it.
No, that's because we have only the cycle problem. We are only doing left forks. Now we have to do right forks also, right? So I'm saying they picked up this. Now what will happen? One will try picking up the right fork. Okay, fine. Then you're saying 5 will pick this up.
Then five can finish it.
Okay, so there is no deadlock. So that's excellent. So 5 eats and puts this thing down. Okay, and then one can pick up this thing. Okay, okay. So then one can pick up this thing. Okay, and then one starts eating. All this happens. Then let's say 3. But 3 can already eat, right? There is no problem for 3. So 3 can keep eating anyway.
1, 3 and 5 are given the left fork and the right fork, they should do it as an atomic operation.
What is an atomic operation?
I mean, when suppose 1 takes up the left fork, before 5 can take up his left fork, he should take up his right fork. That means they should be done concurrently, and no other process can come in the middle.
So
I mean, they should be
No.
done as atomic operation.
no, I am assuming. See, that's why I have broken this up into smaller and smaller grains. And I'm saying that finally, if there is one action called pick up left fork, which I assume is done atomically.
If I break up in between, then deadlock can't be avoided.
Then show me that there is a deadlock, right? If you're saying deadlock can't be avoided, then there is a deadlock, right? So show me where it.
In this case, when 1 picks up and 5 picks up,
Yeah.
then none of them can, then 1 cannot eat. But 1 has engaged the fork number 1, so even 2 cannot eat also.
Yeah. Yeah. So okay. So all I'm saying is it's not as though this solution is perfect, right? But at least we are seeing some progress, right? At least one person gets to eat, right? So is there any possibility at all that there is a deadlock with this algorithm? So that's what you are claiming, that there should be a. So I'm saying, can you exhibit some scenario by which there will be a deadlock?
When they're not atomic.
No, this is what I have assumed. This operation and these two operations are separately atomic. That's all I'm assuming.
Separate.
Yeah.
Left fork, picking up left fork is separate.
And is one atomic action, picking up right fork is one atomic action, right?
So everyone. One cannot eat. And in the meantime, it can happen that 2 actually needs the fork.
Two does need the fork. 2 is waiting also. Everybody is hungry. Everybody is hungry, right? So everybody is waiting for forks. So that's all okay. But at least one person is getting to eat, right? And if one person is getting to eat, and we have said that once that person eats, then there is at least a gap of 30 seconds. Okay, so within that gap of 30 seconds, at least one second person, who I don't know who it is, but somebody will start eating, right? Then once this person finishes eating and there is a gap of 30 seconds, within that the third person will start eating. So so there is there is no starvation, right? Whoever wants to eat eventually gets to eat, right? We are not saying they get to eat very fast, okay, but at least they get to eat. Right? And we are only worried about starvation. We are not worried about the time of amount of time it takes you to get to eat, right? Okay, but there is a problem with this solution. It's not a very big problem, but it is a problem. What is the problem? Think of these as some jobs which are there, okay. There is a problem which actually which will not occur among the philosophers, but this will occur in an operating system. Okay, so supposing I am a job, okay, I mean, so I need some resources, so I execute some code, right, to get there. The code basically looks like this, right? Okay, so do I execute this code or do I execute that code? which code should I execute? Yeah,
Question is not clear.
I'm saying these two statements occur in this order. Here they occur in the reverse order. So there is some code here. Inside this code, these two things occur in one order or they occur in different order. So these are two different pieces of code, right? If you think of this as some function which you are calling in the operating system, okay, then this will be one function 1 and the other thing will be function 2. So when I am a job and I want a resource, should I call function 1 or should I call function 2?
I will just do modulus of philosopher number and
No, but now there are no philosophers, now there are only jobs. That's why I said this actually does.
job number.
Huh?
I will do modulus of job number. If modulus of job number is 1, then I will do the left then right and it's 0 then.
Okay, so first thing I need to do is from the operating system, I need to actually get what is my job number. Okay, but it might happen that there are 5 of us trying for the same resource and all of us have odd job numbers.
It depends on because it will not depend on the job number, but rather how many philosophers are there on that job. It will depend on that.
Correct,
Job number.
correct. So who is going to maintain all this? Right. So normally we say the operating system maintains all this, but now we are the operating system. You see the difficulty. Yeah. So it's so this is a little. So basically, it needs maintaining some kind of data structure. Okay. For instance, maybe when you want a resource, then you I mean there's a counter or something, and so you say you get it. You look at the value of the counter and increment it. Something like that you do. So then you know that you are number 1, somebody else is number 2, somebody. Okay. So you have to find some solution to this, but you have to find the solution yourself. Okay. There is nobody else to help you, right? So you have to figure out some way of doing that. Okay. All this we require because we are pretending to be the operating system itself, and there is absolutely there is this raw hardware below us. There is nothing else which can help us. Right? So, okay. Okay. So it looks like this solution works. Okay, with some extra work. Okay. So can we prove that there is no deadlock inside the system? How do you prove that there will be no deadlock? Okay. So show me a contradiction. So suppose there is a cycle, then so it's not a very easy argument, but it's also not very difficult. Basically, you have to argue with the fact that numbers are odd and even, right, and show that the cycle can always be broken. Okay. So I don't want to do that argument right now, but it's a good exercise worth trying to show that this is actually correct. Okay. Okay. So this is what we can guarantee is that this solution is deadlock free. There is no deadlock, and you can then argue that it is starvation free. Okay. So which means that no philosopher ever is hungry and waiting to get some fork and does not get it at all. Right? Both these things we can argue. So we will do this a little formally later, but at the moment these are the two properties which we are looking for: deadlock freedom and starvation freedom. and this is one solution for that. Okay. So the characteristics of this solution are that it's I mean the characteristic of this solution is that it is asymmetric, right. I mean the odd numbers do something else and the even numbers do something else. Okay. So this is an irritating thing for an operating system. An operating system would like, when you make a supervisor call, you make a supervisor call and you don't worry about function 1 and function 2 and this kind of thing, right. So what you would like is a symmetric solution to the dining philosopher's problem. Okay. We want a symmetric solution. So what would be a symmetric solution? Where all the processes, the code that they execute is identical. Now if you want to put it in the form of a story, then you say that the philosophers are too busy thinking, they never notice whether they are 1 or 2 or 3 or 4 or 5. Okay. They just go and sit at their table and eat and come back, but they don't know. They just look at the table, eat. They don't even know whether there's somebody at the left or right or okay. If the fork is there, they pick it up. If the fork is not there, they wait. If the fork never appears, they starve, they die. Yeah. Can we number the forks? Yeah, that would be one way of doing it. But then I'll make the philosophers not read the numbers on the forks also. No, these are all. We are just really speaking, we are looking for a symmetric solution, right? I mean, the solution which the case suggested is an asymmetric solution, right? So depending on whether you are odd or even, so you have to check whether you are odd or even in some way. And depending on that, you have to execute different pieces of code. You don't want that. You want to execute the same piece of code whoever you are. Yeah.
How about using calling technique? Instead
How-
of busy way, you poll.
Yeah.
So suppose if anyone who wants to use the fork wants to eat, will have to first send out a poll to see if their respective forks are available. And if suppose two people are asking for the same code, then the operating system will have to decide which philosopher gets the fork.
Okay.
That
But-
would probably be based on that.
Okay. But since we are the operating system, we have to decide. How will we decide?
Higher the number, they get the fork.
Yeah, but that means that you look at numbers again, right? So
Always a higher number process gives the higher priority.
So the person who called first can get the
hmm?
The person who called first asked for the fork first gets the
No, you're saying
But both can happen at exactly the same time. No, but let's see. Person who this no when you're saying ask for the fork, you mean this executing this test, right? So you have to record the time at which this test happened, right? So again, that will be another data structure. No, I'm saying, see, it's not that easy to find a symmetric solution. So you'll have to do some extra work somewhere, right? So one possibility is to do to have some table or data structure or something where you actually record some information, right? but that should be something which is visible to everybody, okay, and they should all execute some protocol which they will all follow. Yeah. So there are several solutions which are there, but none of them are entirely satisfactory. Okay, one solution is that there is a butler. Okay, there is a with every such this thing, the philosophers always have a butler, and then the butler decides. Okay, so now you can say this is like asking for the operating system, but but we are the operating system, and we decide that for our contention of this particular resource there will be this butler. So what will the philosophers do? The philosophers will go and tell the butler, I want to eat, and the butler will give them the force, put them on the table and get them to eat, and then the butler can follow some algorithm and can follow round robin, whatever you want. Okay, the butler can follow some algorithm, and on that basis everybody will get to eat. Okay, so such a solution is said to be centralized. Okay, but what we might ask for is a distributed solution, which is where there is no central process like this, right, like a butler or somebody would say. So now we strengthen our requirements and we say we want a solution which is symmetric and which is distributed. Right. How do we do this? Right. So you can see that this is a very simple problem. I mean, as I said, it's not like Byzantine generals where everybody is maliciously doing something. Nothing of that kind. This is all very straightforward, honest people going and doing their operating system. But even handling such a simple thing, okay, becomes a difficult when you actually try to implement it. Okay, and these are all very reasonable things. You see, why is this? Why do we say a centralized this thing is not good? Okay. Yeah, and this is for contention to one particular resource, and an operating system may be handling, who knows, thousands of resources. So you will have one butler for everybody, right? So it's an expensive way of doing it. So you want to avoid that. So you want to say that why don't you let the user jobs themselves come up with some protocol which will work, right? So that's this requirement of distributedness. Requirement of symmetry, as I said, the user job should have only one supervisor call to make. They shouldn't have a choice of supervisor calls to make. These are all extremely reasonable things which you expect. So how can we solve this problem like this? Well, this is a So these two computer scientists, Daniel Lehman and Michael Rabin, I think it's double N. They proved a theorem showing that the kind of solution which we want, the kind of ideal solution which we want, does not exist. Okay, there is no solution which is deterministic, distributed, and symmetric. and but of course they also proved that there is a probabilistic, distributed and symmetric solution. Okay. What is a probabilistic, distributed and symmetric solution? A philosopher, when he or she wants to eat, then tosses a coin and decides whether to first pick the left fork or the right fork. Okay. So now of course there is a zero probability sequence that all the philosophers will simultaneously, their coin flips will turn out to be such that they will all first pick up the left fork, okay, and so on. So basically you try to pick up the left fork, okay, and after some time, if it's, you wait for some time, if it's not available you put it down, then you toss the coin again, after you pick up the, and you keep doing this, okay, until you get. So so with probability 1, okay, this solution is deadlock free and starvation free. Okay. But and as I said, this is just one piece of code which is executed. So you make a supervisor call, right, and the supervisor call will basically look at some random variable bit and decide on that basis how to proceed. Okay. So again I don't want to do the proof for this. This is again not an easy proof, and you have already seen some proofs like this. Did you look at the impossibility of consensus proof? The Fisher, Lynch and Peterson's proof showing that it is impossible to have consensus under some conditions. Did you see that? No, you haven't seen that. So maybe I should do one of these proofs. So this is a proof which shows that certain, if you expect too much out of your algorithm, then unfortunately no such algorithm exists. Okay. So of course normally we do not, I mean, you may think that normally operating systems don't opt for this thing. Okay. So what they do is instead they compromise on this. Okay. So we have the kind of asymmetric solution which he was talking about, right, which is that you keep track of some number, and then depending on that value of that number, somebody picks up the left fork and somebody else picks up the right fork. So that's easy to implement inside an operating system. Right? You just require to fix one number beforehand, and you look at that, you take tokens out of, I mean, pick up that number, increment it, look at the last bit or something, and decide that this is what you want to do. So this is, so actually the solution which you said is the solution which is used. Okay, but that solution, that is, I mean, there is a good reason for that, is what I am trying to say. It's because we know that there is no solution of the other kind, right? Okay, but this was, we are talking about problems which arose in the 1960s. Okay, and these days people go in more for probabilistic solutions. Okay, so for instance, supposing you want to make a call, let's say, I don't know, you want to call somebody in New York. Okay, so how will your call be routed? Okay, so so maybe there are two ways, or maybe more than two ways of doing it. You will go through, the call can go through, I don't know, Delhi and London and then New York, or it can go through Singapore and Sydney and Los Angeles and New York, or some. So there can be many ways of routing a call, right? So what would a telephone company do for routing a call? Okay, what telephone companies do is they toss a coin. They do it probabilistically. So they know that. So if I don't know on what parameters they decide, but let's suppose that the Delhi London route has higher capacity, so there is more possibility of routing the call there. Then they will say with 0.9 probability I will route the call this way, with 0.1 probability I will route the call via Sydney, etc. Okay. Why do they do this? because again there is a theorem like this. There is a theorem which shows that if you follow a deterministic policy, then the chances of a traffic congestion are very high. Okay. So if you want a congestion free telephone call, which is what users want, okay, then there is no deterministic solution. Okay. So you have to use a probabilistic solution. Okay. And so they do the routing probabilistically. Okay. So these days you find a lot of such things. I mean, if you look at, say, how the internet is implemented, it heavily uses probabilistic algorithms. Okay. This kind of things rely a lot on probability. So, finally, let us come to the implementation of this statement. Okay. We have this operation called pick up left fork, and of course, in an operating system there are no forks and things like that. So how do you implement this? Okay.
So now if you pick up a lock, no one else is allowed to use your exclusion list. So if
Yes.
you are using it, you say that this is mine, no one else is allowed to use it for as long as I have it. When I free it, you also free the lock, so then someone else can take that lock.
Okay. Okay. So you're saying use a lock. Then how do I test this?
If it's not locked by another process, then it's free. Then it's on the table.
I see. So you require a lock which you can lock, which you can unlock, and which you can check whether the lock is locked or unlocked, right? You want three things. For instance, let's say Java, if you write your code in Java, Java has a lock this thing, but it doesn't allow you to test a lock. You can either lock or you can unlock, right? You can't do anything else. Okay. So, maybe what I am saying is wrong, in the sense Java provides so many kinds of locks that there may be some other kind of lock which actually provides these three capabilities, but the thing which I am familiar with just allows lock and unlock, two operations. So, okay, but ultimately we are going to come down to the same question. Let's suppose there is a lock routine which is provided by Java. How does Java implement that lock?
You have one bit. If it's say like 1, then it's locked. If it's 0, then it's unlocked.
Okay.
It's actually the opposite in, operating system sense. When it's 0, it's locked.
Sorry, yeah.
It doesn't matter, whichever way it is, how does it matter? It's a convention which we decide, no? So, whether 0 is locked or unlocked is something we decide. So yeah, but now how do you execute? What if two people want to lock at exactly the same time?
Then the locking operations should be atomic.
Okay.
So only one person can lock at a time. I mean the total locking operations is done in atomic space. Otherwise, two can access the same ball.
No. See, here is a bit, right? So let's assume instead of bit, we'll assume a byte or a word or something, and let's say that here is this last bit that has to be set with 1 or 0 or whatever. So you'll execute some statement like OR with 1 1 1 1 1. This is the kind of thing which you'll do. This will be like setting the lock. Right? At the hardware level, this will be like setting the lock. So I execute an OR 1 1 1 1, etc. Okay. You execute an OR 1 1 1 1. Bit becomes 1. So I think I have the lock. You think you have the lock. Okay. And then we both try to do something.
value the calculus means that has secured to them.
Who manages the process IDs? Distributed computing, okay, here we have an operating system, but in distributed computing, typically you are sitting here in, I mean, the very simple example, I'm sure you have come across this before, which is you take some railway reservation system and there's some train and there is a last coach of that and the last berth on that, and I am trying to get up that berth and he is trying to get that berth, okay, and somehow the ultimately one of us will have to get that berth, right? How do you decide at that point? Okay, right? So the way it is done is my request is, so supposing it's a train originating in, I don't know, Central Railway whose headquarters is in Mumbai, then my computer will send a request to Mumbai, his computer will send a request to Mumbai. In Mumbai that computer has an operating system, that operating system finally will actually make that decision. Okay, so right, and depending on that, then communicate the decision back to whoever it is, saying you have got the berth or you have not got the berth, right. So ultimately it comes down to some one CPU, let's say, okay, or deciding this. But what if you now have a multi-core processor where there are several CPUs trying to access the same this thing? How do they know? Right? So these problems keep occurring over and over again. I mean, although they first occurred in 1960s, okay. Why 1960s? Because in 1960s there is a device called a channel which was invented at that time, and what this channel does is if you have your main memory and you have a CPU which is accessing the main memory, and you have some device, some IO device trying to access the main memory, then this channel allows the IO device to take data from the memory. So both the CPU and the IO device are trying to can have access to that word. The idea was that because IO devices are very slow compared to CPU, right? So the CPU just says, okay, transfer this thing to the printer or something like that, and then the this channel actually does the transfer slowly. Meanwhile, the CPU is busy doing other things, right? That is the first time that this contention was introduced in 1960 because of a hardware invention, okay, and that is once contention was introduced, all these problems came up. And all these problems like dining philosophers and various other problems came up, right, which people found solutions for. Well, Dijkstra's solution was, Dijkstra said the solution I will use is the following. I mean, Dijkstra thought in a very original way, and for instance, all of us encounter these kind of problems in computer science. But it takes somebody like Dijkstra to think of philosophers and thinking and eating and model it in a completely different way. So a solution also involves the concept of a semaphore, okay, and a semaphore, if you don't know what it is, I doubt whether you have seen these kind of things. Only people of my age would have seen this, okay, So when I was a kid, then railway signals looked like this, okay, and this thing is called a semaphore. Okay? This thing which goes up and down, that's called a semaphore. Okay, and when a train has to enter some piece of track, then this is green. It means it can actually enter that piece of track, and this is red. So this means that the train has to sit here and wait. Okay. So this operation of I think, okay, so this is called P and this is called V. I hope I am correct. Yeah. So this P and V comes from Dutch words because Dijkstra was a Dutch person, which stands for this signal being down and the signal being up. Okay. So basically the way I think about it is this means pass. The train can pass. Okay, this is something Dutch as far as I am concerned. Okay, so the Dutch word is also, the Dutch word for this is passeren. which means that the train can pass. And this is some complicated word which I don't understand. Okay, so what is a semaphore? Okay, a semaphore is a natural number, or if you like in C terminology, it's unsigned int, right? This is what is a semaphore. Okay, and so you have two operations. So PS and VS on the semaphore, right? For standing for. Okay, what does this mean? This is yeah. So what P means is that I mean, this is actually going to be an arithmetic operation, right? But I am saying the meaning of that arithmetic operation, which we will interpret it to mean, okay, that you have to wait until the semaphore is not set, which means that, and if the semaphore, and after that you set it. Okay, and when you say unset the semaphore, this assumes that the semaphore is set, because if the semaphore is unset, then you don't unset it, right? So basically this means something like this, if you want to imagine it, that wait until this signal is red. Okay, so you can imagine the train here. This is how trains looked like in my days. Okay, and so the driver comes here, waits until this signal looks like this, and the driver goes up there, pushes this down, and then takes the train through. Right, this is passing. Okay, and V means set this signal back to the red position. Okay, so this is so there used to be one lever out here, so you would basically yank that lever and that would move this signal up there. Okay, so anyway, so this is so Dijkstra used this metaphor of a semaphore or a train passing on a single line section, okay, to actually solve this problem. Okay, so he said basically there is a semaphore for each fork. Okay, so here you would do a P on the left fork. Okay, so now he eliminated this whole busy wait. So here what you would do, so his solution is the following: get left fork is you do P on left fork, get right fork is you do P on the right fork, put down is you do V on the left fork, okay. So the question now is, how do you implement this P and V? I mean, okay, I can call it P and V, but finally I have to do it in some machine friendly terms, right? Okay. Okay, so the V operation is S is assigned S plus 1. I have to remember this. I might make a mistake here. Let's see. How should I remember this? Okay, if we assume 0 and 1, then this will anyway make sense. So let's assume this is going to vary between 0 and 1. So this amounts to setting from 0 to 1, and what we are talking about is here wait until s equals 1, right. So now if you like, if you want a busy wait implementation of this, this will be basically what we had written earlier. Okay, we wait until some variable is, we do a busy wait checking until the variable is 1, okay, until the bit is 1, and then when the bit is 1 you make it 0. Okay. That corresponds to your taking this semaphore, or you are taking the resource. Okay, and so this piece of code will, but what does wait until this thing mean? Okay, now if I write this busy wait code here, then this code will keep on executing all the time. Every 30 seconds this will keep on executing, and you will exit from this only when you have acquired that resource. Until then you are just waiting, that's all. Okay. Instead, which is of course an inefficient way of doing this, because you are using, if you remember that all this was invented in the days of single processor CPUs, right? Yeah, so they just weren't, I mean there was no multi-core, nothing was there, right? So at that time you can't have this processor just keeping on doing this busy wait, then the other guy will get to do nothing, right? The other process will also, so you want, so the way this was implemented was that there would be a queue. There would be a queue data structure, okay, and what this would mean is that you actually put yourself on the queue, okay, and then pass control to the other process, okay, and then the other process would start executing, and when the other process was through, it would say I am through, it would set that bit, and then this and then say let the next process be taken off the queue. Then from the queue you pick up the next process to be executed and you start. This is how this was managed. Okay, so you need a complicated data structure, namely a queue, to actually do this. Okay, it's not just, what I'm saying is it's a very simple operation, but this wait until operation, to actually implement it you have to do something, and either you do a busy wait, which is kind of worthless in a single processor environment. So what you do is you actually have a queue instead. You maintain a queue data structure where this waiting is actually implemented. Okay. So this is how they actually solved this. So Dijkstra in 1968, Dijkstra and many others, they wrote an operating system which is called, very modestly called, the operating system. So and so the stands for Technische Hochschule Eindhoven, which is where Dijkstra worked. Okay, so that's where he, so it was, and he actually used these ideas. I mean, he didn't use dining philosophers, but he used the idea of semaphores. Semaphores are actually used in this operating system, probably for the first time. Okay, so, and it's actually quite a beautiful paper to read. This paper, it's available in several collections, or you might even find it on the web somewhere. The essential idea which he used, and that's now you probably study it in any operating system course, but this he used for the first time, is to say that there is something called a kernel, and then there is a layer on top of it, and then there is a layer on top of it, and so on. So this was first, this came about in this THE operating system. So Dijkstra did this, and then he used, basically semaphores was the only means which he used to actually do this. And on the basis of, now of course managing these queues and all is a very is not very easy, right? So the crucial thing which you want to do is the following. You want to say if s equals 1, then s is to be set to 0. Okay. So if you translate this into hardware, right, then this basically means load this s into the register, check if it is 1, okay, and if so, do this. Okay. But this is many machine code operations, and while you are doing this, somebody else could also be doing this, right? So the other process could also be executing exactly the same bit of code. This is two different processes. That process finds that s is 1, this process finds that s is 1, that process is set to 0, this process is set to 0. Then there is all this confusion as to whether that process has the resource or this process has the resource. So Dijkstra realized this problem, and he suggested that this thing should be made atomic. Okay, there should be one hardware instruction which should do this. Okay, and so there is this instruction called test and set. So he recommended to the hardware manufacturers that this be there. So after some time later, Dijkstra went to work for one company called Burroughs Corporation, and there he helped them with the design of their some machine, and they incorporated this test and set instruction in their hardware, and since it was very useful, then others also started using it, and now I think practically every machine has a test and set or some comparable. It doesn't have to be test and set, it can be some other kind of thing using which test and set can be implemented. Okay, so now there are many, this kind of machine is actually there in the hardware. Okay, so Dijkstra, of course, I think in 1972, Dijkstra got the Turing Award, which is the highest award in computer science, and not just for this. I mean, he did many other things which he was known for, and this is something which, but I would say these are all extremely important contributions. The whole idea of how to run this kind of situation, how to manage resources, this was really a kind of, shall we say, a very clean solution to these problems was worked out by Dijkstra. I mean, there are many solutions, it's not that his was the only solution, but his solution was so clean that everybody then started using it. So now these kind of ideas are used in any operating system, they are taught in operating system courses and so on and so forth. Yeah. So anyway, so this is what I planned for today's lecture. So I am a little early. So I just want to give you one problem to think about. So I have a buffer, okay, and what I want to do is so there are two processes, okay, and this is the only way of communicating things from one process to another. Okay, so what I want to do is I want to put one bit here, okay, and then that bit, whatever that bit is, that should be picked up by P2. Okay, so this is called producer-consumer problem, or it doesn't matter what it's called, right? So ultimately, you want to put one bit here, and you want that person should take it away. Okay, but you want, okay, but now when you put 1 here, okay, so then let's say that person should get the 1, okay, but this guy should know that that guy has taken the 1, because only after that this will put the next bit might be 0, because if you put here first 1 and then 0 and then whatever 1 or something, that person might not get all the bits, right. So you want actually the bits to be given to you in a sequence, and you want to know that that bit has been communicated from, let's say, from left to right. Okay. So how do you implement this? And the only thing I will allow you is semaphores. Okay. You use semaphores to implement this. Okay. You assume that these semaphore operations are implemented somehow in the hardware, okay, and it is a fact that they can be implemented using the test and set and so on. Okay. So using semaphores, how do you implement this? So this is a very, I mean the general producer consumer problem is much more complicated than this. This is just a very straightforward version where there is only one producer, one consumer, and a 1-bit buffer. There is nothing else. Okay. So this is something you can think about. Another problem, which is so this is called cigarette smokers problem. I know it's not supposed to be good for me to be telling you all this, but I'll put up a health warning if you like here. Right. So so this was invented by Suhas Patil. Okay. And okay, so the basic idea here is the following, that there are processes which are smokers, I mean, okay, and there is a process which continually supplies matchboxes, and there is a process which continuously supplies light, lighter or whatever. No, not a light. A light meaning probably, how will it supply light? Actually, not, maybe cigarette paper. Let's see. So the idea is that you need several things at the same time. Okay. So you need to take or tobacco. Let's say. So there is something which gives you tobacco. There is something which gives you say a paper. Okay, and then there is something which gives you matchboxes, and you have to collect all this and roll up a cigarette and light it and then smoke it. I mean, so the question is, how do you manage all these resources? Okay, so this is slightly more complicated than dining philosophers because there are like more things to manage now. Okay, so you imagine that this keeps on happening forever. Okay, there are processes which keep doing this forever. How do you manage this? So basically, smokers want to smoke forever until they die. I mean, that's the idea. So that's the thing on which this is based. Okay, so that's a version, a slightly different variant of this dining philosophers kind of situation. Okay, so that's something you can think about. Producer consumer problem is by somebody called, I don't know his first name. His surname is Courtois. Okay, I don't know what their first name of this person is. Okay, and yeah, Suhas Patil, I don't know what happened to him. He did his PhD at MIT and then disappeared. Okay, we'll stop with that. Thank you.